LEDs don't get their color from their plastic covers. Instead, the color of the light comes from the materials inside the semiconductors. Hello, my name is Ned Johnston. I'm a third year chemical engineering student, and today we're going to talk about introductory material science concepts that went into the invention of the blue LED. This will be mostly a surface level examination of the crystal structure and material science concepts that we've learned in this class. All references will be made available at the end for you to continue your journey if you're interested. In 1962, General Electric created the first red LED. A few years after that, engineers at Monsanto created a commercially viable green LED. But for decades, all we had were those two colors. So LEDs could only be used in things like calculators and watches. The world's engineers were looking for the blue LED. Then, we could mix red, green, and blue to make white, and every other color, unlocking LEDs for every type of lighting, from light bulbs to phones to computers and TVs. Everyone knew that LEDs had the potential to replace light bulbs because light bulbs are actually really bad at making light. They work by running current through a tungsten filament which gets so hot that it glows. But most of the input energy comes out as heat. Only a negligible fraction turns into visible light. In contrast, LEDs primarily create light, so they're far more efficient. When you have an isolated atom, each electron in that atom occupies a discrete energy level. We learned about this concept of the atom in Chemistry 1 and 2, our freshman year of university. You can think of these energy levels like individual parking spots for electrons. All atoms of the same element, when they are far enough apart from each other, have identical available energy levels. But when you bring multiple atoms together to form a solid, something interesting happens. The outermost electrons now feel the pull not only of their own nucleus, but of all the other nuclei as well. And as a result, their energy levels shift. In Chapter 18, Electrical Properties of our textbook, William and David, the two authors, describe this phenomena as an energy band. The highest energy band with electrons in it is known as the valence band, and the next higher energy band is called the conduction band. In conductors, the valence band is only partially filled. This means with a little bit of thermal energy, electrons can jump into nearby vacancies, and if an electric field is applied, they can jump from one vacancy to the next and conduct current through the material. In insulators, the valence band is full, and the difference in energy between the valence and conduction bands, the band gap, is large. So when an electrical field is applied, no electrons can move. There are no available vacancies to move into in the valence band, and the band gap is too big for any electrons to jump into the conduction band. This brings us to semiconductors. Semiconductors are similar to insulators, except the band gap is much smaller. This means a few electrons will have sufficient energy to jump into the conduction band, and now they can easily access nearby vacancies and conduct current. Not only that, the vacancies they left behind in the valence band can be filled by other nearby electrons. By themselves, pure semiconductors are not that useful. To make them more functional, you have to add impurity atoms into the crystal lattice. We learned about this in Chapter 4, Imperfections in Solids, with a concept known as doping. For example, in silicon, you can add a small number of phosphorus atoms. Phosphorus is similar enough to silicon, so it easily fits into the crystal lattice, but it brings with it one extra valence electron. So with a bit of thermal energy, these electrons can jump into the conduction band and conduct current. Since most of the charges that can move in this type of semiconductor are electrons, which are negative, this semiconductor is called N-type. There's another type of semiconductor, and it's called P-type. To make P-type silicon, you can add a small number of atoms, say boron. Boron fits right into the lattice, but brings with it one fewer valence electron than silicon. So it creates a vacancy just above the valence band. And with a bit of thermal energy, electrons can jump out of the valence band, leaving behind more vacancies. It is this behavior that is responsible for the carrying of current in P-type semiconductors. Where things get interesting is when you put a piece of P-type and N-type together. Without even connecting this to a circuit, some electrons will diffuse from N-type donor to P-type acceptor and fall into the vacancies. This makes the P-type a little negatively charged and the N-type a little positively charged. Electrons will keep diffusing until the electric field becomes so large that it prevents electrons from flowing. If you were to connect a battery the wrong way to this diode, no current would flow. But if you flip the polarity of the battery, electrons would freely flow from N to P. This behavior, known as forward bias, is a hallmark feature of the diode. So roughly, here's how an LED works. When an electron falls from the conduction band to the valence band, from higher energy to lower energy, that band gap energy is emitted as a photon. The energy change of the electron is emitted as light. The size of the band gap determines the amount of energy and the color of the light emitted. In pure silicon, the band gap is roughly 1.5 electron volts. Moving up the spectrum, you can see why the first LED were red, and then green, and why blue was so hard. We learned in physics 2 that blue light requires more energy, and therefore a larger band gap. Glossing over much of the history and advanced material science behind repeatedly failing and eventually successfully creating the blue LED, engineers in the 1990s found the right material and revolutionized the modern world. The design started with a sapphire substrate. Building upwards, gallium nitride was followed by N-type gallium nitride, which was created by doping the gallium nitride with silicon and germanium. Following that, there was an N-type aluminum gallium nitride and indium gallium nitride, P-type aluminum gallium nitride, and finally P-type gallium nitride, which was created by doping gallium nitride with magnesium. You can see here some of the 3D models of each individual crystal structure and begin to imagine the length that engineers went to invent the blue LED using concepts we've begun learning in this class. As we wrap up today's discussion, it's incredible to think that the concepts we've begun learning in this class, like crystal structures, point defects, doping, annealing, semiconductors, and so much more, can bring to light something as crucial to everyday life as the blue LED. I'd like to remind you to continue being curious. I've provided links to videos and academic works that helped create this presentation. Thank you.